Real gases. What are real gases? Well, we've been talking about ideal ones, so these are like the ones that are not ideal, which is all of them. Okay. Most gases don't appear like they don't behave regularly. They just don't. They're real life. They have all kinds of crazy little quirks. And so when we're talking about ideal versus real gases, the idea here is that in order to behave ideally, you would be accustomed to fitting into this equation, which is pressure times volume equals nRT. In an ideal world, this PV over nRT always equals 1. Well, that's not what happens. So if we plot this versus pressure, an ideal gas would follow this line. So what you're looking at here now is a plot of how gases should behave versus how they really behave. All right, we can kind of compare this to children, I guess. Some behave ideally in some situations, like this right here, where you've got this orange line is behaving pretty close to the dotted line, just for a smidge, and then it starts veering off course. Okay, same thing here. All of these different molecules, they behave ideally for a tiny amount, and then they don't behave anything like an ideal gas. And so what we can do is from this, we can figure out some certain times where gases behave slightly ideally, and then they just start to go off the rails. And so when do they behave best? Okay, at low pressures, and which makes sense. If you pressurize a molecule, now you're going to force them to do all kinds of interactions that they wouldn't have otherwise wanted to do. And so at these really low pressures down here, it's going to behave pretty ideally. And then the other choice is at high temperatures. Notice how this is 203, this is 293, this is 673. And so at really high temperatures, it's going to behave more ideally. But why is that? Remember all of those rules from the kinetic molecular theory that we talked about? The idea that they never attract, that volume of particles can be assumed to be 0. Well, there's a reason that at low pressures, it's going to behave well, because if molecules are not forced to be close together, then they're not going to have time, or they're not going to be located in close proximity to each other where they're going to start to interact and affect the motion of each other. If you've got a high pressurized environment, now the size of the gas is going to matter compared to the size of the container. And at higher temperatures, they're moving around so fast, they're not going to have time to attract. At lower temperatures, they're moving around slowly, and they're going to find each other and interact and affect the motion of the things around it. And so it's because of these laws of this kinetic molecular theory and the assumptions, which are inherently flawed, that the ideal gas law is not ideal, and instead we need to perfect it, make it a little bit better, not perfect it, okay, but make it a little better using this corrected ideal gas law, which is now called our real gas law, okay? So the idea here is instead of having P equals nRT over V, we could have an adjusted P. So what is this adjusted P? This adjusted P says, hey, that volume, the volume of the container is dependent on how close stuff is to each other. And so if we subtract the volume of the individual atoms or molecules from the volume of the container, then we're going to more regularly represent the true volume that is available for gases to roam. And so this correction factor of B is simply a way of taking our volume and correcting it for the space, the size of the atoms. So if I were to ask you, what is B? What is this B correction factor? That is a volume correction factor to account for the volume of the gas atoms. Okay? So what's next? The next thing we need to account for is the attraction between molecules. And so we do this with A. A is going to be our pressure correction. What's happening is the greater the pressure, the more these guys are kind of smooshed together, and so the greater the attraction. Or you can read about in the opposite, where the attraction between molecules lessens with the number of collisions that would occur within the sides of the container. And so this A, I like to think of it as like the attraction constant. It considers the attractions the molecules feel, and it's going to change that observed pressure. And so in doing this, if we substitute in this equation we just made, and we substitute that in over here, and we solve, we're going to get this new fancy equation. Where the idea is it's still the same. We have pressure, but this is corrected pressure now, times volume, but corrected volume equals nRT. So this is still PV equals nRT. Nothing has changed except for we've added in a random volume correction and a random attraction correction, which corrects our pressure. All right, so how do we use this? So here's kind of a summary slide that talks a little bit about what we just discussed. The idea is at high temperatures, molecules have a high kinetic energy, so they're moving around lots and fast. At low pressure, molecules don't collide as much and therefore don't exert pressure on each other. And so those are the concepts behind this attraction pressure correction and this volume correction. Where do we get this A and B from? This table. All right. I would never expect you to just know A's and B's off the top of your head. Okay. I would give you this table and I would say, all right, this is the status of pressure, volume, gas constant, temperature, solve. And then pick a variable. Okay. So I'm giving you all of these variables except one, solve for the other. Okay, but you can't think about these conceptually. So if A has a low, so if helium, for instance, it has a very low A, what does that mean? Because it's really small compared to everything else. It means helium is not naturally attracted to other things, which it's not. It's very content with its nice 2 little electrons there. Okay, whereas something like water is very attracted to other entities. And so you'll notice some different things here. So all of these, for instance, are your noble gases. What happens as you increase the number of electrons? Because this has the most electrons here of xenon, and helium has the least. So as you increase your number of electrons, you're increasing the attraction. That makes sense. Throw some more electrons on, throw some more ways you can interact. Same thing here. Hydrogen, go all the way down to here. What happens? We're increasing in size. What happens to our attraction? It's increasing. And you can do similar stuff here. And then same thing as you're kind of looking at this volume correction. We've got a lot more volume to account for with xenon than we ever would with helium. Now, obviously, it's not perfect, but this is something that has been determined and or theorized, depending on which way they did it, experimentally or theoretically. And so we can just substitute in this value for A and that value for B. But do notice all you do in order to figure out your A's and B's is find your chemical and then locate its A and B. So I want you to do that. I want you to try to do this one on your own. You've got 9.858 moles. So everywhere you see an N, you write down 9.858. It's argon. So that tells you should be looking at your argons. Oops. And then it's maintained at a 0.846 volume. So there's your volume at this temperature. And then it asks you, what's the pressure in atmospheres calculated using, and this is also another name for this real gas law, is the van der Waals equation. They're kind of synonymous. So this is what we're looking for. So go ahead and give this a try on your own. You know your gas constant, you know your temperature, you know your volume, and now you know your correction factors. So give it a try. If you did this correctly, your pressure equals 275.9 atmospheres.